In today's section, we're going to learn about two more shortcuts for proving that triangles are congruent. So if you guys remember, again, and you want to keep track of what you have learned, remember that when you want to compare that triangles are congruent, the longest way is to prove that the three angles on the one triangle have a corresponding and congruent three angles in the other triangle, and then the three sides in one have three sides in the other that are corresponding and congruent. But in the end, you're going to need to prove that three sides and three angles match, okay? And so that's a lot. You don't always have three sides and three angles. And so then we started the whole thing about, well, what about shortcuts? Do we need all three sides and all three angles? And we learned that there's a shortcut called side angle side, which is two sides, right, and the included angle. And if you can prove that two sides and the included angle are corresponding and congruent, then you can prove that the entire triangle is congruent one to the other. So that was our first shortcut. Well, today we're going to learn two more shortcuts. We're going to learn side, 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 and we're going to learn hypotenuse leg. Now, hypotenuse leg is special because it only works for right triangles, and we'll talk about that. But after today, you'll have three shortcuts to prove triangles congruent. So side, side, side congruence theorem says that if you happen to have three sides of one triangle that are congruent to three sides of another triangle, then the two triangles are congruent. So if you notice, in this one, we see that side AB, we see that segment AB is congruent to ED. We know that side BC is congruent to EF. Notice the tick marks. And we notice that side AC is congruent to FD. And so what happens is, because we have the matching and the corresponding sides, and we have all three, we know that those two triangles are now congruent to each other. And so we want to make sure that we label it correctly if I have to write that they're congruent. Like I might start with, when I write it, I may say triangle, and if I'm going to say it, remember I got to have the corresponding parts. So notice I go from A to B across the single tick mark, right? A, B. That's similar to, for example, D to E, right? And then I'm going to go from B to C, which is going down the second tick mark. So triangle ABC is going to be congruent to triangle D, E, and F. And again, make sure that your angles work out and that your vertices and stuff like that, that they basically follow the same order. So in the next example, we're going to talk about deciding whether the congruent statement is true. So they're not saying whether or not the triangles are congruent. They're talking in this one, is this congruent statement true? If these are congruent to each other, and you notice that they are, notice you've got the one tick mark, the two, and the three. So this would be a side, side, side congruence. These are definitely going to be two congruent triangles. Now, how do I know for sure that the statement is true? Well, I need to actually look at the statement and make sure that the parts work. In other words, DF, it's the first two, that segment has to be congruent to HJ. So I go to the picture. DF is this one, and HJ is that one. Notice they both have two tick marks. We're good. I go to the next one, FG and JK. FG is congruent to JK, and I come over to here. FG and JK are congruent to each other, so that works. And then the last one would be, for example, DG is congruent to HK, and I look at my drawing and I see DG, HK, they are congruent as well. And so this is a yes, the congruent statement is correct. And for the explanation, you can just show me that the corresponding segments are actually congruent to each other. Now I come over here and they say again, decide whether the congruent statement is true. I'm not even sure if these shapes are congruent, right? So how do I know? Well, again, I do the same pattern. I say, well, is AC congruent with CA? Well, notice anything is congruent with itself. That's reflexive property, so that would be a yes. Okay. Then I go to the next one and I'm like, okay, CB and AD. So I come over to here. CB is 7 units long and AD is also 7 units long. So yes, they're congruent. So I'm on the last one, never stop short, check them all. AB is congruent to CD. And I go to my drawing and I look and I see that AB is 3 and CD is 4. Well, guess what? It's not congruent. And so therefore, this congruent statement is not valid. Okay, and the reason it's not valid, the explanation would be, basically this is enough of an explanation. I can see that one of the segments, the corresponding segments, is actually not congruent. And that would be the end of that. So no, those two triangles are not congruent to each other. Here's the third one. Again, decide whether the congruent statement is true. By looking at the picture, I know that these two triangles are congruent because of side, side, side. Now I need to just see, does this statement match those pictures? Are the letters in the right order? Did we do this right? So again, you're going to say, well, if this is correct, then QP must be congruent with RS. So QP here is congruent with RS, this line. So yes, that's right. They both have 2 tick marks. Then PT goes with ST. So PT here and ST here. Notice they both have 3 tick marks, so that goes together. And then QT and RT. So I come over to here, QT and RT, notice the single tick mark, they're congruent. So yes, that's my explanation, and my answer would be yes, the congruent statement is true. Again, I keep going here. It's just, I think there's something missing from this slide, but bottom line is they're just talking about why the bench with the diagonal support is stable while the other one, while the one without the support can collapse. And so what happens here is, again, we're talking about really physics and stuff. And the only thing I would tell you is triangles. If I have a rectangle, I don't know why that closed like that. If I have a rectangle and I have a triangle and I put force here right on the center of the rectangle and the triangle is a much more solid structure, okay? The rectangle will collapse. It'll either collapse in the middle or these things will shift over and the whole thing will kind of fall over. And so structurally, a triangle is much better for support. And you'll notice in a lot of buildings and things like that, you see a lot of triangles that are used in bridges and in things, in a lot of structural things. Triangles are like a big deal. The next one is going to get us to the HL theorem that we talked about, which really pertains strictly to right triangles. So the first thing I'm going to have to do here is go over the vocabulary associated with a right triangle in the first place. A right triangle, again, is a triangle where one of the angles, or the largest angle, is 90 degrees. So I know that this is a right angle, which makes this a right triangle. Now, in a right triangle, you're going to notice that there are 2 legs or 2 sides that make the right angle. Well, those 2 sides that make this angle are called the legs. And so this is different than isosceles triangles. Isosceles triangles also have legs, but the legs are the equal sides, right? There's the base side and then there's the 2 legs. Here we have legs as well, but the legs are not always equal. They could be the same or they could be different lengths, okay? The other name for a side that we have is the side that is opposite the right angle, and that's known as the hypotenuse, okay? That's known as the hypotenuse. That's right here. And the hypotenuse is the longest side of a triangle, of a right triangle, okay? Notice it has nothing to do with it doesn't touch the right angle, because that's reserved for the legs. It's opposite the right angle, and again, the hypotenuse is its name. Only a right triangle has a hypotenuse. And so that's why the HL theorem that we talked about only applies to right triangles. And you might say, well, what does HL have to do with a right triangle? Well, let's go to our next slide. The HL theorem. And notice the HL theorem says that if the hypotenuse and a leg of one right triangle are congruent to the hypotenuse and the leg of another right triangle, then the two triangles are congruent. So again, here we've got, let's say, this triangle, we've got this one, and you know that these are 90. And if I tell you that this leg and this leg are equal, and I tell you that this hypotenuse and this hypotenuse are congruent, then you have enough information to prove that the two triangles are congruent. So the HL theorem would tell you that the hypotenuses are the same and the legs, one leg is the same, okay? And so H stands for hypotenuse and L stands for leg. And that's why this only works for right triangles. Only right triangles have a hypotenuse in them. In this problem here, what you're going to be doing is you're going to be graphing both of these triangles that they gave you. The vertices is -3, -2. Right here, that's J. 0, -2 is K. And -3, -8, which sadly goes off the page here, is down here. And so you notice you're going to have JKL, which happens to be this right triangle. Notice I have a vertical and a horizontal side, so I know they meet at 90 degrees. When I go to the other triangle, I go to 10, 0, I go to 10, -3, and I go to 4, 0, and I draw it out. And again, another right angle here. So it says graph the triangles and show they're congruent. Well, if I just count the sides, I know that this side here is 6 units long and this one is 3. And I know that this one is 3 and this one is 6, because vertical and horizontal lines are easy to tell. So I could actually prove these triangles are congruent for many reasons. Notice I can prove it using side angle side. I've got a side, another side, and the included angle, and I have it for both, a side, and the included angle. So side angle side can be used. I can use side, side if JK happens to be the same as, and this one here is R, this is S, and this is T. So if I find the length of LK, okay, and I find the length of ST, if they're the same, I know these two triangles are congruent. And when I do the math, you're going to see that they are the same. When I do all the math, and I'll go back and do that, it's going to be the square root of 45, which is 3 radical 5. And this one's going to equal the square root of 45, which is also 3 radical 5. And therefore, I know that these two triangles, because this one and this side would be equal as well. So side, side would also work. And because it's a right triangle, once I know the hypotenuse is 3 radical 5 on both, and I know that there's a pair of legs that match as well, hypotenuse leg can also be used. And so, of course, I would have chosen side angle side only because that was the easiest one to do. I didn't have to find the hypotenuse to find side angle side. But again, it's just knowing that there's multiple ways sometimes to prove that two triangles are congruent. Sometimes none of the methods work, sometimes one method works, and sometimes multiple methods work. In the problems we're going to be doing, what you're going to usually only need to prove it one way. And obviously you want to prove it the easiest way. In this problem, obviously we had our easiest way. Let me just real quick though, before we move on to the next slide, let me show you how I found the length of LK. Let me just make sure that I remind you how to do it. So if I'm trying to find LK or KL, right, I know that, let's say L is -3, -8. Let's say K is 0, -2. Remember that the formula for the distance between those 2 points is going to be the difference of the x's, -3 - 0 squared, plus the difference of the y's, -8 - -2 squared. So when I get into this, I get -3 squared plus -6 squared. And when I do that, I get the square root of -3 squared is 9, and -6 squared is 36. 9 and 36 equals 45. And then how I simplify it, I know that 45 is 9 times 5. The square root of 9 is 3, and it leaves me with 3 radical 5. And so again, that's the same process for ST. Again, for ST, if I look at the original problem, the difference of my x's is 10 - 4 squared. The difference of my y's is minus 3 minus 0 squared. And again, you notice that you get 6 squared plus, sorry, negative 3 squared, and you're going to get 36 plus 9, or square root of 45. And so that's how we got to that, okay? Moving on to this one here, again, they're asking us, is there enough information to prove the triangle's congruent? Now, I know it's hard to read, but they're talking about triangle FGH and triangle HJK. Now, again, to prove that these triangles are congruent, I'm going to need to know that the corresponding parts match, right? So I need to see what I've been given. Notice that I have a right triangle. So, and I have two sides that are congruent. I have side GH is congruent with JK. Well, notice that this is a leg and this is a leg. And then I have side FH is congruent with HK, and these are my hypotenuses. And so notice that I have a matching hypotenuse and leg. So then this would be a yes because of the HL theorem. And so again, I do have enough information. I have my hypotenuse and a leg, and I'm good to go with this one. And the last one is a proof. And these proofs are a little bit challenging when you have these two triangles that overlap. Me personally, I try very hard to kind of get used to doing them together. But when I do separate them, I separate them a little different. You know, I kind of draw the one triangle, and then I sort of draw it a little bit away. And then when I do the other triangle, I sort of like to do that triangle with the same angles. And notice here, they flipped it. So for me, if I was to rewrite this here, it would be, the right angle would be there, this would be X, this would be Y, and this would be Z. And I would kind of write it with the correct orientation as opposed to this one here, which is a little bit flipped, okay? But anyway, so once I have my triangles, and I know exactly the two triangles that they're referring to in this problem, it's time for me to start thinking about my proof. Ultimately, they want me to prove that triangle WYZ is congruent to triangle XZY. Now, I haven't named this because given it a number because I don't know what step it's going to be along the way, but I know it's the last thing I'm going to write. I know the first thing I'm going to write is going to be pertaining to these two sides that are congruent. It says that side WZ is congruent to segment XZ. So WY is congruent to XC. When I go to the picture, I want to identify that for myself. WY, whoops, not that one, sorry. WY, it's this diagonal, okay, is congruent to XZ. So these two lines in red are equal to each other. In my separate pictures, I know that it's this and this one, okay? It's the two diagonals. Notice that it's also the hypotenuse here, and it's the hypotenuse here, okay? So the next, so this is my reason for this one obviously is just given. When I go to the second thing, I see that WZ is perpendicular to ZY and XY is perpendicular to ZY. So I have two lines here that are perpendicular. So when I go to my drawings and I find WZ and ZY, I see that it's telling me that this angle here is a right angle because definition of perpendicular lines tells me that they meet at a right angle. When I go to XY and ZY, again, it's the same thing, which tells me, again, that this is a right angle. Now, I listed that it was the hypotenuse because I already had the right angle marks down here. However, if those angles weren't listed, I would have had to kind of have identified that first to be able to call that the hypotenuse. Okay, so again, this is given. Okay, I might, have something here like saying, maybe, I don't know that I would ask you to do this, but if I was really doing a really thorough and complete proof, I would probably here have to say that angle WZY and angle XYZ are right angles. And really, I know that those are right angles because of definition of perpendicular lines. I know that they meet at right angles, okay? And then I would probably even take it a little further and say that triangle WZY, well, let me say the triangle in the proper name that they have, is I would say that triangle WYZ and triangle XZY are right triangles, okay? And again, that would be definition of right triangles, okay? That if you have one angle that's right angle, then it's a right triangle. Again, I don't know that this is essential, but I think it's kind of important to say it because, again, in the original picture, those right angles weren't there, and I feel like that's probably something that should be in your proof, okay? So anyway, put that in the proof. Now we know that we have those diagonals or those hypotenuses are equal. So we know these are congruent to each other. And then we look at the next thing that they're asking us. They're asking us to prove that the triangles are congruent. So I have the hypotenuse. I know it's a right triangle. And if I could just prove that one leg is equal to the other, I would have enough information to prove this. And so when I look at this, anytime I have a shared side, that's an equal side or a congruent side. So I know that ZY here is going to equal YZ here because, again, it's a shared side. So number 5, I'm going to say that ZY is congruent to YZ. How do I know that? Well, when a shared side basically utilizes the reflexive property. It says that the side equals itself. Okay? So now I have, notice, I have a leg and a hypotenuse in one triangle and a leg and a hypotenuse in the other. So I now have enough information for me to say that my two triangles are congruent. So this step down here, let me just rewrite it. Triangle WYZ is congruent to triangle XZY. And how I know that it is congruent, what told me that it's congruent, is the fact that I applied the HL theorem here. Notice I have, this statement tells me that the hypotenuses are congruent, and this statement tells me that the legs are congruent, or one leg. And I have everything I need to apply hypotenuse leg. And this part tells me that it's a right triangle, which is the only one that hypotenuse leg works for. So that's really the gist of it. I mean, if you had pretty much left this out, okay, this extra stuff here, this would have even been still an okay proof. It would have gotten you most of the credit because really I think this was just being a little bit more specific about the fact that it was a right triangle. But when you have the hypotenuse, you have the leg, the HL theorem, you really have everything you needed to insert here. Okay.